I'm very happy to introduce our second speaker, Jonathan Wunderlich. He's going to tell us about computer-assisted existence proofs for Navier-Stokes equation on an unbounded strip with an obstacle. Thank you, Jonathan. Go ahead.
Yeah, thanks for this kind introduction, and also thanks to the organizers for giving me the opportunity to talk about my research about this Navier-Stokes equation on an unbounded strip. This is joint work with my supervisor, Michael Plum, who also gave a talk in the CRM-CAMP seminar in this series. And first of all, I would like to give some short outline of my talk. I want to start with some background information about the Navier-Stokes equations we are considering. And as a second part, I have this computer-assisted part where I present the existence and enclosure theorem and give some details in the assumptions needed for the theorem. And finally, I want to give some first results and an outlook on the future work which is still to do in this section here in the Navier-Stokes equation. So let us start with the background information. So we consider the incompressible Navier-Stokes equation on an unbounded strip, which is perturbated by some compact obstacle D. So we have this domain omega, which is let me mention that this is an unbounded domain. And we have on the right hand side here this forcing term F, which is a function in L2, and we have the Reynolds number here. And since we want to apply the techniques presented by Michael Plum in his talk in the CRM-CAMP seminar, we make an ansatz for this function V here as follows. We said V should be of the form Brazil flow plus some function U bar, where U bar tends to 0 as x goes to plus or minus infinity. So at infinity, we assume that our function is somehow the Brazil flow. And inserting this into the equation, we get these additional terms here. And what is some kind of nasty, we get this splitted boundary conditions at the boundary of the obstacle, where U bar should be equal to minus the Brazil flow, and we have the 0 boundary condition at the rest of the boundary. And to get rid of this splitted boundary condition, we introduce a second transformation with some function V here. So U bar is equal to some function U minus V, where V is equal to the Brazil flow on the boundary of the obstacle and 0 at the rest of the boundary. And we also assume that V tends to 0 as x goes to plus or minus infinity. And using this ansatz, again, we get this transformed Navier-Stokes equation where we have this term gamma here, which is Brazil flow minus our function V. And also we have this 0 boundary condition on the whole boundary of omega. And let me just mention that here in the right-hand side F, we have absorbed some terms which are independent of U. And so this F here is actually not the forcing term from the beginning. So just mention to keep in mind that this is not the forcing term from the beginning. And then we are looking for weak solutions in space H, which is the divergence-free subspace of H10. And since this is used in several computer-assisted techniques, we need to rewrite this as a zero finding problem. So we define an operator F by the weak formulation of our Navier-Stokes system. And let me just mention, since our test function phi is in H, we can eliminate the pressure from our equations by using by using integration by parts, and so the pressure is eliminated. And then we end up with the following equivalence. U solves our transformed Navier-Stokes equation if and only if U is a root of this operator F. And before coming to the assumptions for the existence theorem, let me just clarify the setting again. So we have the space H here, which is endowed with this inner product here to make it as a Hilbert space. And by phi, we denote the isometric isomorphism corresponding to the inner product. And from now on, we suppose that we have an approximate solution of our transformed Navier-Stokes equation, which means that we have an approximate zero of our operator f. And let me note that for the computation of this approximate solution, no verified computations are needed. We just need usual numeric algorithms to compute this approximate solution. And with this approximate solution at hand, we can define the linearization of our operator f at this approximate solution, which will be denoted by L in the following. And looking at the talk by Michael Plum, we need several assumptions for our theorem. So we assume that we have constants delta, k, and k star in hand, such that delta is a bound for the defect of our approximate solution. And moreover, we assume that k is a norm bound for the inverse operator of L, which is this assumption 2. And by this assumption, we get that L is 1-to-1. And in the proof of our existence theorem, we also need that L is surjective, which in recent works can be achieved by this assumption 2, since the operator phi inverse L was symmetric. And this is not the case in our Navier-Stokes. We have no symmetry here. So we need another idea to get the surjectivity of our operator L. And therefore we assume that we have this constant k star for the adjoint operator, which now leads to injectivity of this adjoint operator, and then surjectivity of our operator L. And with this assumption in hand, we can formulate our main theorem, which reads as follows. So we have this approximate solution here, and we have the constants delta, k, and k star at hand, satisfying these assumptions A1 to A3. And then if we can verify it with integral arithmetic that this product here, 4 times k squared, c4 squared times the Reynolds number times delta is less than 1, then we can prove, or then there exists an exact solution in our space H of our transformed Navier-Stokes equation, which satisfies this enclosure result here. And let me just mention that this bound here, or this assumption, which needs to be verified or needs to be hold true for our theorem, is also a demand on the accuracy of the approximate solution. So if delta is small, we can expect that this assumption here, or this is satisfied. And furthermore, when we have proven this, the existence of this u star here, then by retransforming by gamma, we get a solution to the original Navier-Stokes equation here. And let me now just go into some details about the approximation and the defect bound. Since omega has to be an element in our space H, we need divergence-free finite elements which guarantee that our approximate solution is exactly divergence-free, and therefore we need or we use a divergence-free finite element space based on Argyris elements. And moreover, we compute the defect bound delta with the same techniques presented by Michael Plum in his talk, so I don't want to go into further details here. These are the same techniques. So now we have to talk about the computation of the norm bounds k and k star. Let me just mention that the computation of the norm bound k star for the adjoint operator is quite the same. So I just talk about the computation of k and k star is similar. And as I already said, this operator phi inverse L is non-symmetric in our Navier-Stokes case, and thus non-self-adjoint. And so in recent works, this for computation of this constant k here, they used spectral decomposition arguments, and we cannot use this here since we have non-self-adjoint operator here. So we need another idea to get rid of the, or for the computation of this constant k, and we square this inequality here. So we end up with the computation of lower bounds for the spectral points of this eigenvalue problem here. And therefore, especially we have to compute lower bounds for the essential spectrum and for the isolated eigenvalues, if such isolated eigenvalues do exist. If not, we just set the eigenvalue bound for equal to the bound for the essential spectrum, and then we can choose our constant k to 1 over square root of the bound for the eigenvalue. So in the following, I just want to go into further details about the computation of these two spectral bounds here. First, I would like to start with the computation of the bound for the essential spectrum. And let me just remark that by construction, our finite element solution omega is compactly supported. And we can also choose our function v, which was to get rid of this splitted boundary condition, can be chosen compactly supported, since our obstacle is compact. And so we can use compact perturbation arguments to get rid of these compactly supported functions omega and v in our essential spectrum computations. And moreover, we can show that we can consider the eigenvalue problem on the whole strip, since this obstacle doesn't affect the essential spectrum. So if we consider the strip without perturbation by the obstacle, we can compute a bound for the essential spectrum of this eigenvalue problem here on the whole strip without obstacle to get a lower bound for the essential spectrum. And when you just have a look at this definition of the operator LS, there is no compact function here. This omega and v are gone, and we are on the whole strip. And then we can use Fourier transform in x direction and Fourier series expansion in y direction to compute a lower bound for this essential spectrum here. So what remains is the computation of some bound for the eigenvalue, lower bound for the first eigenvalue if it exists. And therefore we use the well-known Lehmann-Görisch method together with a homotopy method to get the lower bound lambda 1 bar here, which is our bound for the eigenvalue. And then we have all the assumptions for our existent theorem. And finally, I just want to mention first the first results we made. So for small Reynolds number, we have some verified bounds here. And let me just mention that for higher Reynolds numbers, the bound for the essential spectrum, so if the Reynolds number decreases, the bound for the essential spectrum decreases. When the bound for this, when the Reynolds number increases, the bound for the essential spectrum decreases, and so this makes the computation difficult for higher Reynolds numbers. So, but this is a goal for future work. We want to compute this for higher, or proof existence for higher Reynolds numbers. And what also is a goal, we want to do this for different obstacles, especially for obstacles which are not on the boundary of the strip. So that we have a boundary obstacle inside the strip. And we also want to reconstruct the pressure. We'll just note or recall that we eliminate the pressure by our ansatz with the divergence-free subspace. And finally, we want to reconstruct the pressure and also want to prove some error bound for the pressure. So that's all from my side. Thank you for your attention.
Thank you very much, Jonathan. Well, we have plenty of time now for questions and comments, discussion.
So I have one question.
Yeah.
So about what you mentioned at the end about the putting a different obstacle.
Yes.
So what are the differences there? Is this just that maybe the flow is more complicated, so you need a bigger computer, or are there also theoretical obstacles, things that change in the math really?
I expect no change in math, so that's why we use this no formulation with stream functions in our computations. So that's first part. For there's no change in math, hopefully, but we expect that since there are more re-entrant corners when the obstacle is inside the flow, so we hope that we can get approximate solutions with accurate enough to get an error bound which is small enough.
Okay, I see. Thank you.
Yeah, I do have another question for, so you mentioned you wanted to do some proof for your Reynolds number. Do you believe there will be some bifurcation theory appearing if the Reynolds number is high enough?
We haven't considered this yet, some bifurcation theory about this. It would be in future work to consider also bifurcations, but we hope that we can extend this for higher Reynolds numbers and then go to bifurcation. Yeah.
Okay, thank you.
Can you hear me?
Yeah.
Yeah.
Okay. So one question is that, so in this proof or nice proof, so is there any assumption about the regularity about the solution? For example, solution belongs to H2. You see, if the domain is already non-convex domain, and around the corner, how about the affection about the singularity?
You mean for the exact solution or for the approximate solution?
Maybe the final result, or during the proof, inside in the proof. So is there any assumption or a condition that so everything can be done just, for example, only the information on H1?
So our approximate solution omega needs to be in our space H exactly. So let me just go to the space. So our approximate solution has to be in this space here. So it has to be in divergence-free, exactly divergence-free solution or approximate solution, but in H10, so not more.
I see. So is there any difficulty to process the singularity?
Singularity at re-entrant corner, or
singularity? Yeah.
Or what do you mean with singularity? I don't get.
You see around the corner.
You mean to use some singularity function at the re-entrant corner, or?
Yes.
I don't expect that this is possible since we need this divergence-free condition. So we thought about using corner singularity functions at this re-entrant corners, but since we need to have an approximate solution which is exactly divergence-free, I think this is not possible to use corner singular functions here.
Okay, great. Well, I suggest we thank the speaker again. And